Okay, hi everyone. So this is your lesson on exponential functions. And the first thing I want to make sure we recognize is how we know that a function describes an exponential function, not a linear function or a quadratic function or an absolute value function. And I think you see that when you're looking at an exponential function, the x value is part of an exponent. Right here are examples of the exponential functions that we will study. But as you can imagine, in maybe 2 years in calculus, you will be exposed to functions that look a little bit more hairy. Maybe the function looks a little like this, you know? Um, okay? But if I look at this function right here, and this exponent here is the absolute value of x cubed minus the absolute value of x, you'll notice that here, the x is still involved. It is still in the exponent. This too is an exponential function, okay? Now here's what gets really interesting. Let's say I add this guy, okay? Now I have what's almost, I call these like these weird hybrid functions. That's kind of exponential. It's also kind of quadratic. And those functions like this kind of defy categories. They have characteristics of, several families of functions. There's no real name for functions like that have features of many. I call them like mathematically biracial functions or something like that. But that goes above and beyond us here. The point being, for us, how do you recognize a function as exponential is answered by just merely looking at where the independent variable or the x is, okay? So first things first, what I'm going to have you do is let's take a look at this one here, okay? And you're going to see us exercising some of our work with negative exponents. What I'd like you to do is go ahead and fill in this t-table, if you will. And we're going to use calculators if you find that you need to. Whoops, what am I doing? I don't think you're going to need to, though. Okay, I'm going to give you these x values here. Okay, so go ahead and fill that out and then replay me. Okay, so these are the y values that I got. Okay, and then what I want to do here is I'm going to go down low and I want you to plot these points right here on an xy axis, and I'll meet you there. And I plotted some points. Let's see, what did my scale is 2, as you can see here, okay? And so what I didn't get in here, I didn't get the negative 224. I guess I could do that. Negative 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, so negative 224 is way up here. And I guess I could, if I wanted to, put in, maybe x equals 10, right? And if x equals 10, the y value is going to be 6 divided by 2 to the 10th. 2 to the 10th is going to be some huge number. 6 divided by some huge number, as we can imagine, is going to be a number really, really close to 0. And I hope you recognize here that in this case, as x gets bigger and bigger and bigger, right, y is going to get closer and closer and closer to 0, but it's never going to actually hit 0. Now I'm going to try to take a steady hand here and try and sketch this. Okay, and I'll sketch it. Let's see if I can do how good of a job I can do. I'm going to sketch this. Woo, ooh, ooh, ooh. Okay. And sometimes when you miss your dots, you just make them bigger. This is the general symbol that I get, the general graph that I get, okay? Now, we've called a line that a curve gets closer and closer and closer to. This is our second time seeing this. We definitely see this behavior that as x gets huge, y gets smaller and smaller and smaller and smaller, and it approaches this horizontal line y equals 0. And there you see one of the defining characteristics and features of exponential functions. They have horizontal asymptotes. They have one horizontal asymptote. I can see Dylan asking the question, when we look at this behavior here, at some point, does this slope become almost vertical? I guess we could say you want to think it would, right? Because it tends to get much, much higher, but no, this doesn't actually ever get vertical. This does get wider in the left-hand direction the more negative I go, okay? So first things first, interesting, exponential functions have a horizontal asymptote. I want to bring your attention, I'm shrinking down deliberately here for a second. I want to bring your attention to this, the y-intercept, okay? The y-intercept, as with all functions, occurs at x equals 0. And when I look at this function here, I will notice that x equals 0, right, turns the base here. The base of the x is the 1/2. The base of the x is not 6, but 1/2 to the 0 is 1. So y equals 6. The y-intercept at x equals 0, it is absolutely the case that for exponential functions that we will see, right, these very straightforward basic ones, this y-intercept when x equals 0, that 6 value, yeah, it corresponds to this 6 value right here. That is definitely not a coincidence, right? That 6 value and this 6 value, okay? The other thing I'm noticing is when we talk about an exponential function, when we talk about that entity which is raised to a power, we call that the base, okay? The base of this exponential function is 1/2. And I'm going to just make sure we are just taking a little bit of a tour down really a distant memory lane. Okay, that's the same thing as 0.5. I'm going to notice something. This number is less than 1, okay? Which means what we're looking at here is something that's losing 50% each time, right? It's unlike the interest rate question we had yesterday. In this case, we've got something that is diminishing as x increases. Okay, because the base is less than 1, we're calling this an exponential function that is decreasing. And while we can go to a party and say, oh, it's an exponential function that is decreasing, we can also use the proper labeling and called it an exponential decay function. Okay, it's an exponential decay function. Okay, because again, we're looking at the base. The base is that number, or numbers, if you will, that which is raised to the exponent x. Okay. Sometimes in contextual problems, when you are looking at the y value when x equals 0, you may see the phrase initial value. Okay, when you've got an initial value, when something asks you about an initial value, that is the value of something at the initial period of time. Okay, and sometimes if time is represented by x, what initial value is referring to is, something I like to call it sometimes like the starting value. Okay, or quite frankly, it's the amount when t equals 0. And here I know that I've used x, but t equals 0, t is often an independent variable, and you know that t is sometimes a stand-in for x equals 0. In fact, everyone, if I went and made this t here, and I were to ask you to think about, like, what's a real life situation of this model here? Let's see. Maybe this is, I don't know, like the number of warts on your foot where t is in months. So, where t is in months and the number of months since quarantine. So let's say March. So let's say if t equals 0 is March, that means at the beginning of March, what do you have? You have 6 warts. And at the beginning of April, what do you have? You've got 3 warts, right? Yeah, okay, so 6 warts at the beginning, then 3 warts, then 1.5. The number of warts is decaying by 50%, right? I mean, it's kind of a gross, but I guess somewhat realistic. I don't know. I mean, warts are a part of all of our lives, I guess. Okay. All right, let's take a look at the second function, y equals 2 to the x. I'm going to move over here. And I maybe am noticing something. I wrote this as y equals 2 to the x. you know, I could have, if I really wanted to, I could say, let's write this as y equals 1 times 2 to the x, because maybe you're saying to yourself, well, you know, she had it written in this form before, you know, maybe you want to have it written in this form. All that's fine. Okay. And I want you to go ahead and make a t-table. And this is where I'm going to have you choose a t-table that is going to be reasonable for you all. I'd pick reasonable values for x and y. And let's find the y values and then replay me. Okay, so I just picked these values. I didn't get too ambitious. I kind of used what I used in my previous t-table. And then I'm going to go ahead and plot these points. I'm going to do the best of my ability, and I'm going to keep a scale of 1 here for my graph. Let me go and try and do that, and then you can replay me. And this is what I've got here, right? And once again, you see this asymptotic behavior, right? The asymptote is still at y equals 0. The difference is that this function approaches y equals 0 as I head to the left, right? Okay. And you again notice kind of this characteristic shape, right? So what you're looking at here in both cases, this is kind of the general shape of an exponential function. It kind of has this interesting bend to it, right? I'm going to think to myself here, if I have any generalizations that I can make connections with, I'm noticing here the initial value, right? The value in x equals 0 is 1. Right, so this point here is 0, 1, and I'm noticing again that there is a generalization to be made, right? Okay, that is again the y-intercept. Now I'm going to ask you here what you think about nomenclature. We called this an exponential decay function. Let's see. This would be an exponential growth function. Okay, now let's make sure we say y, exponential growth function, because what is the base? The base equals 2, right? And 2 is bigger than 1, okay? Now, if the base equals 2, that's the same thing as 200%, agreed? So in a situation like this, if the base is 200%, that means the rate of increase, this is something whose amount is increasing by 100%. Remember what we said, 100% just means status quo. You maintain the same amount, right? 100% is equal to 1. So we're talking about 200%. 200% means that something is growing by 100%. Sometimes when we have situations where the base is 2 or when the rate of growth is 100%, we call it a doubling situation, like a doubling time situation, where every period of time that's elapsed, the quantity doubles. I often think of like the fertilized egg in the womb. Like it's, you know, you start off with 1 cell, and then it becomes 2, and then 2 becomes 4, and then 4 becomes 8, right? That's kind of what I think about here. Okay. Let's see. Then we get to, I think I have a nice, all right, here we go. 50 times 0.92x. Let's go over here, and this is one that's going to require a calculator only because obviously we're not going to have raised 0.92 to the third power in our head. But what I do want you to think about before we even go start graphing it is, what will this function look like? Well, let's see. The base is 0.92. That means it's less than 1. So are we going to have exponential growth or decay? Okay, answer that question. I am going to ask you for the y-intercept, right? What is the y-intercept? You're going to fill that in before you even make a t-table. And then what I want you to write is the equation of the horizontal asymptote. And I often do HA for horizontal asymptote. Fill these 3 items in just here in words before we proceed. Okay, so because the base is less than 1, we have an exponential decay. So right away in my head, I should be making this kind of motion in my head. I know it's going to look something like this, right? It's going to have this kind of behavior, that kind of image, right? Okay, it's going to look like that because that's what an exponential decay function looks like. The y-intercept is going to be 0, 50, right? I've seen that there are some generalizations that can be made, right, with exponential functions in this form. And the horizontal asymptote is going to be the line y equals 0. So right away, that allows me to go down here and just kind of put some things in place. I may not be able to, I may not be able to make it perfect. I won't have all the details yet, but I can say that I'm going to have y equals, so 10, 20, 30, 40, 50. I'm going to call this my point 0, 50. So my scale is 10. I have a horizontal asymptote at y equals 0. And I generally know that an exponential decay function has this general shape. Okay? Let's just add this exponential decay, and what amount am I losing with each change in x? I'm losing a percent with each change in x. I'm losing 8% with each change in x, okay? Now what I'm going to do is just have you give me maybe a couple values to the left and to the right here. Maybe plug in x equals 1, x equals 2, plug in x equals -1, -2. And, oh, my calculator has walked away with my son. In any event, when you find those values, you should get basically a sense of a graph that's going to look like this, which is not surprising given our work thus far. Okay? Very good. Okay, so I think I'd like you to please look at page 52 in your book and look at question number 486. Okay, and I'll meet you there. Okay, so this is number 486, and this is question A. Now, if we read together here, it says, find a plausible equation, plausible means believable or reasonable, reasonably accurate, of the form y equals a times b to the x for each of the exponential graphs shown below. Okay, let's just do this one together. Well, let's see. First of all, I'm noticing that it's an exponential growth function. Okay, so what that means is at the end of the day, my base here should be bigger than 1. That makes sense. I'm going to use the fact that I see a 0, 1 here. Okay, that already tells me then when I plug in x equals 0, I should get y equals 1. But I also have seen that, I've also seen that that value, that y value, is also this a value. So right away, I'm going to make some progress here and say this is the same thing as this. Okay? Or I can just simplify and do this, right? So now the question becomes, how do I find b? Maybe some of you can eyeball this, and maybe some of you can see like, oh, well, I can see what b has to be to make this equation true. Maybe some of you cannot. And the natural question is, well, how do I do this in the math way? How do I do this in a very rigorous, clear way that doesn't leave me victim to just guess and check? Well, let's see. 1, 3 means at x equals 1, y has to equal 3. So I'm going to pull this information down here. I solve for a, so I'm very happy about that. When x equals 1, y has to equal 3. Well, that means 3 has to equal b to the first. Well, b then must equal 3. So I have just found the equation of this exponential growth function, because the base here is 3, we've got something growing by 200% each period of time x. Okay, I'm going to leave you to do the second graph, which is an exponential decay. Well, let's do the second graph together. Why not? Second graph together. Okay, so we're on B now. And I'm going to meet you there. Let me get my graph up. Maybe you're going ahead of me. Go right ahead. I'm going to set myself up here while I'm waiting, or while you're waiting. But go ahead. Maybe you're moving ahead of me because you see the question right there. -1, 1, 2, 3, 4. Okay, so here this value is -1, 5. And I've got, oh, interesting, 0, 2. And the graph is definitely showing me the horizontal asymptote is at y equals 0. And you're wondering, Ms. Yam, is the horizontal asymptote always going to be at y equals 0 for an exponential function? And I'm going to say to you, well, if we start talking about vertical shifts, maybe not, right? But right now we're talking about basic exponential functions, no shifts yet. And also if you look at your book, I think they do a reasonably good job of trying to really show you and make clear that with these 3 exponential functions, the horizontal asymptote is absolutely at y equals 0. Okay, here's what I've got, and maybe you've worked ahead of me and you have gotten yourself set up already. This is the form that you are asked to find. Oh, I'm definitely using the fact that I know A has to equal 2. Okay, this is going to be interesting. So that means that 5 equals 2 times b to the negative first. Look at that. So then we have, let's see, 5 divided by 2 equals b to the negative first. Oh, I love this. Don't get lost in the details, everyone. We've got to figure out what b is. Okay, well, maybe you're wondering to yourself, I just learned yesterday that b to the negative first means 1 over b, right? So how do I solve for b? Many of you will probably say cross multiply. I'm just going to do the steps out. Why not? Ah, look what I found. I just found b equals 2/5. So we have just found the equation of this exponential decay function. Perfectly fine to leave the base as 2 over 5. Maybe some of you are wondering, well, 2 over 5, can I write that as a decimal? Sure you can. 2 over 5 is equal to 0.4 to the x. So this is a pretty interesting. This is clearly an exponential decay function. Look at this base down here, 0.4, which is 40%. That means that we are losing 60%, right? So all of this makes sense, all right? All right, you are all set for your homework tonight on exponential functions. All you have to do is please do that problem set that's associated with this lesson, and I will tell you to now enjoy your drop day tomorrow, Friday, and the next lesson will be up on Monday. Great job, everyone. Thanks.